So previously we were thinking about the general curvilinear coordinate, something like this. So each coordinate axis is defined as Q1, Q2, Q3 as a unit normal vector along the direction. And if you change the coordinate in, say, Q1, something like this, if there's a change of coordinate is TQ1, then the actual change of distance is some H1 times TQ1 with a scale factor H1 is given as name as metric or scale factor. And this H1, H2, H3, so say DL, Q1, H1, and the one thing we have to remember is that this H1 is not, it may not be a constant, but it can be also a function of Q1, Q2, Q3. Q1, Q2, Q3, TQ1, TLQ2 is H2, Q1, Q2, Q3, TQ2, TLQ3 is H3, Q1, Q2, Q3, TQ3. So this can be actually seen from this very simple example of polar coordinate. Say this is theta, then if this is rho d theta, right? So if this is rho 1, then this is rho 1 d theta 1, right? So the actual distance along this d theta is different depending on the position, right? If this is located from rho 1 from the origin, then this differential distance is rho 1 times d theta 1, and of course this is, if this is rho 2, then you can say this is rho 2 d theta 2. And for the gradient, gradient is the ratio between the actual distance and change of the function along that position, right? So if there is this is f q1 plus tq1, q2 plus tq2, q3 plus tq3. Say this is f q1, q2, q3. Then the change of function as a change of coordinates is actually, you have to consider that the distance between two surfaces. So say if this is q1 direction, then say if this is q1 direction, this distance must be h1 q1, right? So this is defined as a q1 h1 partial Q1 partial F plus Q2 H2 partial Q2 partial F Q3 H3 Q3. So in Cartesian coordinate, Q1, Q2, Q3 is defined as X, Y, Z, right? And H1 is 1, H2, H3. So for Cartesian coordinate, the gradient, am I loud enough? 거든. Okay. So gradient f x, y, z is x partial x partial y partial z. Circular cylindrical coordinate. Circular cylindrical coordinate. Q1, Q2, Q3 is rho phi z, right? Probably you have forgot what you have learned last week, but you can check my notes. So H1 is still 1, H2 is rho, H3 is 1. So gradient phi, rho round phi, round f, z, round z, round f. Okay, let's save some space here. Spherical coordinate. Spherical coordinate is Q1, Q2, Q3, R, theta, phi, and H1 still 1, H2 is R, H3 is R sine theta. So in spherical coordinate, gradient f r theta phi is r partial f theta r partial theta partial f plus phi r sine theta partial phi partial f. So how many of you are taking electromagnetic theory along with this class? Some? 전자장? So I think they might have been covering this too, right? Not yet? If not, they will. The curl is like a closed loop integral. To say Q1, Q2, say Q3. And let's say center is Q1, Q2, Q3. So doing this integral, so closed line integral in Q1, Q2 plane. Let's say 1, 2, 3, 4. So here, this is Q1, Q2 minus delta Q2 over 2, Q3, and say this Q1, Q2 plus delta Q2 over 2, Q3. So DL1 is H1 DQ1. So say A, B, C, D. So this integral A to B F dl is F Q1 direction, Q1, Q2 minus delta Q2 over 2, Q3, H1. H1 is also a function of Q1, Q2, Q3. So Q1, Q2 minus delta Q2 over 2, Q3, DQ1. So using mean value theorem, we can say F Q1, Q2 over 2, Q3, H Q1. Actually, this must be bar, something like this. And the average value. Q2, Q3 is same. Q1 bar, Q2 minus delta Q2 over 2, Q3 delta Q1. So this is a mean value theorem. How about 3? This is Q1 direction. 3 is opposite direction, right? So C to D is actually minus of F Q1, Q1 bar, Q2 plus delta Q2 over 2, Q3, H, Q1 bar, Q2 plus delta Q2 over 2, Q3, delta Q1. So 1 plus 3 is actually, let me see, can copy, but I like to copy this whole thing and then move it back to the current screen. I think I have to do it again. 1 plus 3 is F Q1 bar Q2 minus delta Q2 over 2 Q3 H1 Q1 bar Q2 minus delta Q2 over 2 Q3 delta Q1 minus FQ1 Q1 bar Q2 plus delta Q2 over 2 Q3 H1 Q1 bar Q2 plus delta Q2 over 2 Q3 delta Q1. So this can be combined then together. F Q1 bar Q2 minus delta Q2 over 2 Q3 H1 Q1 bar Q2 minus delta Q2 over 2 Q3 minus F Q1 bar Q2 plus delta Q2 over 2 Q3 H1 Q1 bar Q2 plus delta Q2 over 2 Q3 delta Q1. But what you can do is actually you can divide the whole thing by delta Q2 and then multiply delta Q1, right? Without changing anything. So it becomes minus partial Q2 partial FQ1 H1 delta Q1 delta Q2. If we multiply by H1 H2 and divide by H1 H2, what you can do is actually you can transform back into something like this. H1 H2 partial Q2 partial FQ1 H1 DQ1 DQ2 H1 H2. This is actually delta S ds, right? So we have done the half of the story. The other half is okay, I'll let you copy this. Give some more time to do. I promised how to copy the previous, like something, and I haven't still figured it out. So, I mean, if I go back, so this is 1, 2, 3. This is 4. A, B, C, D. And we have the center as a Q1, Q2, Q3. So this is Q1. This is Q2. Now here, we have Q1 plus delta Q1, Q2, Q3, right? And along this direction, dl Q2 is Q2 H2 delta Q2. Actually dq2. So this line integral b to c f dl is, because we are now thinking about this, the component of vector along this Q2 direction, so it has to be Q2, right? So we have FQ2 Q1 plus delta Q1 over 2 Q2 bar Q3. Now this is 82 Q1 plus delta Q1 over 2 Q2 bar Q3. H2, same as before, Q1 plus delta Q1 over 2 Q2 bar Q3 times delta Q2. How about 4? 4 is it is going down. It is supposed to be going down, right? So the direction is minus Q2. So minus F Q2, Q1, and this point is actually Q1 minus delta Q1 over 2, Q2, Q3. So actually the significant portion of doing mathematics is drawing pictures, drawing diagrams or something like this. Mathematics is in some way like a drawing. So there is a joke in Korean that 너 수학 시험 잘 봤어? 그럼 그렸어. Right? And that means you didn't do well. Say, normally, in my time, I just 그렸어. How about your time? Yours? Use a similar expression or not? No? So when I was, college was 1980, so about 40 years ago, so maybe the change of expression in 40 years. And an old saying is, in every 10 years, all the scenery is changed, so it must be like changed 4 times, so there may be something. Delta Q1 over 2, Q2 bar, Q3, H2, Q1 minus delta Q2 over 2, Q2 bar, Q3, H2, Q1 minus delta Q1 over 2, Q2 bar, Q3 times delta Q2. So 2 plus 4 is actually same as before, partial Q1, partial FQ2, H2, and delta Q2, and delta Q1, right? So it becomes H1, H2, partial Q1, partial FQ2, H2, ds. You can see it better, I think. Yeah. So let's summarize. It must be like a curve. And you are thinking about this line integral along this path. In Q3 direction, right? The same as this. Q3 normal vector H1, H2, partial Q1, partial FQ2, HQ2 minus FQ1, HQ1 dot Q3 ds. So this is actually Q3 direction, right? So you can figure it out, Q1, Q2. So Q3 is 1 over H1, H2, partial Q1, partial FQ2, HQ2, minus partial Q2, FQ1, HQ1. So actually you can expand it to 3 directions. Let me see, I'll just copy. So you can see some interesting connection, right? 3 1 2 1 2 1 2, right? So this is always true. 1 2 3. So you can guess. So I'll give it as homework. You just check at your home to see if this is true. So you can do the same thing for Q2, Q3 plane and Q3, Q1 plane. Then you can derive the same relationship that called Q1 direction. 1, 2, 3, right? So it must be H2, H3, partial Q2, partial FQ3, HQ3, and minus partial Q3, partial FQ2, HQ2. And Q2, 2, 3, 1, right? This is counterclockwise always positive. You can say H3, H1, partial Q3, partial FQ1, HQ1 minus partial Q1, partial, this is 3. Of course, you cannot see Q3, HQ1. So the curve so you can just write it down. It's very easy to remember that F is Q1. Q1 is always coupled with 2, 3, right? Divided by H2, H3, partial Q2, partial FQ3, HQ3, minus partial Q3, partial FQ2, HQ2. Easy to remember, right? Plus Q2. 2, 3, 1. That's positive direction. So that's the easiest way to remember 3, H1. Partial Q3, partial FQ1, H1, minus partial Q3, Q1, partial FQ3, H3, plus Q3, 3, 1, 2, H1, H2. Always go this way. And the partial derivative is in the same order. Partial Q1, partial FQ2, H2, minus partial Q2, partial FQ1, HQ1. So Q, Q, Q. Easy to remember, right? So let me write it down for 3 different cases. I'm just checking with my circular cylindrical coordinate. Q1 is rho, Q2 is phi, Q3 was 1, H1 was 1, H2 was rho, H3 was 1, right? So curl F is rho direction 1, 2, 3, right? So 1 over 2, 3. 2 is rho, and 3 is 1. So partial 2 is phi, partial phi, partial 3 is Fz, minus partial z, partial F rho, rho, right? H2 was rho. Plus phi is 2, so 3, 1. 3 is 1, H3 is 1, H1 is 1. So this is 1. Partial Z, partial F rho, partial rho, partial FZ, plus Z is 3. So 1, 2 is 1 over rho again. 3, 1. Partial rho F phi, partial phi, partial F rho. And spherical coordinate, you cannot see. So spherical coordinate, but you can I move on? Spherical coordinate Q1 was R, Q2 was theta, Q3 was phi, H1 was 1, H2 is R, H3 is R sine theta, right? So core F. So first coordinate Q1 is R, 2, 3, H2, H3 is R times R sine theta. So R square sine theta, right? And partial theta, partial R sine theta F phi minus F phi R F theta plus theta 3, 1. So 1 over R sine theta, right? So theta phi, partial F R minus partial R sine theta F phi plus phi 1, 2. So 1 is 1, 2 is R, so 1 over R. Partial R F theta minus partial theta partial F R. So we learned how to express gradient and curve in at least 3 different coordinates. So we just learned how to express that curvilinear coordinate, and then that can be actually expanded into 3 different coordinates. And actually, you can expand like up to 19 coordinate system. You can write down gradient and curve if it is needed in the future. But I strongly doubt that you won't need more than 3, unless you specialize something very peculiar design, like stealth jet fighters or something like that. Then you have to worry about different coordinate systems. Next step is, of course, divergence, but maybe you can take a break for a few minutes, right? So, of course, next topic would be divergence. The divergence is something with a change of volume element, right? So say Q1, Q2, Q3. This is 1, this 6. Center is Q1, Q2, Q3. Here, Q1, Q2, Q3 minus delta Q3 over 2. And this point, Q1, Q2, Q3 over delta Q3 over 2. And we are interested in like closed surface integral. In general, we are interested like f ds. This is so the surface normal direction is Q3. Here is minus Q3. So along this surface, ds is actually FQ3, H1, H2, DQ1, DQ2, right? And if you do the mean value theorem, it can be represented as, I'm going to write down this way, Q3, H1, H2, Q1, Q2, Q3 minus delta Q3 over 2. And of course, this normal direction is minus, so you have to put minus 1 here. And bar delta Q1, delta Q2, right? 6 is in upper direction, so 6 is positive Q3, H1, H2, Q1 bar, Q2 bar, Q3, delta Q3 over 2, delta Q1, delta Q2. So since we have some space here, I'll put here 1 plus 6. You can put right this way. Partial Q3, partial FQ3, H1, H2, delta Q1, delta Q2, delta Q3, right? And then you can change it back to volume integral. H1, H2, H3, partial Q3, partial FQ1, FQ3, H1, H2, dV. Right? This is 1 plus 6. 6 is in Q3 direction, so it's positive. 1 is negative Q3 direction, so you have minus sign. So if you add them together, then basically this minus this. If we divide by Q3 and then multiply by Q3, then it becomes derivative, right? And then you can move back to the volume integral using mean value theorem again. So So you divide by H1, H2, H3, and then it becomes DV, volume elements. So if you do other things together, so you can show the other cases. Maybe that's just one page. I'm going to leave it as homework. So closed integral becomes dv h1, h2, h3 partial q1 partial f q1 h2 h3. Let me check. Right. Plus partial q2 f q2 h3 h1 plus partial q3 fq3 h1 h2 dv. So basically this is divergence of V, divergence of F. So if I explicitly write down divergence of F 1 over H1, H2, H3 partial Q1 partial FQ1, H2, H3, HQ3 partial Q2 partial FQ2, HQ3, HQ1 partial Q3 FQ3 H1 HQ1 HQ2. So cylindrical coordinate, circular coordinate system. Q1 is rho, Q2 is phi, Q3 is z, HQ1 is 1, HQ2 is rho, HQ3 is 1, right? So divergence F 1 over rho, partial rho partial, F rho, rho, partial phi partial, F phi and 1 1, partial z partial, F0. Spherical coordinate Q1 R, Q2 is theta, Q3 is phi, H1 is 1, H2 is R, H3 is R sine theta, right? So divergence of F in spherical coordinate is H1, H2, H3 is R square sine theta. partial r partial fr h2 h3. So r square sine theta partial theta partial f theta 3 1. So r sine theta partial phi partial f phi 1 2. So r. Easy, right? So once you figure out how to write the expressions in curvilinear coordinate, you can always write down in different coordinate systems. And one final important expression is Laplacian. Oops. Let me see. Laplacian is very important. The divergence of a gradient. So Laplacian of f q1, q2, q3 is divergence over gradient of f is q1 1 over h1 partial q1 partial f q2 1 over h2 partial q2 partial f q3 1 over h3 partial q3 partial f. So this is your fq1, this is your fq2, this is your fq3, right? So divergence is you have h1, h2, h3 partial q1 partial fq1 h1, h2, h3 partial q1 partial f, small f, partial q2 partial h2, h3, h1 partial q2 partial q3 h1, h2 over h3 partial q3 partial f. So let's just assume that h1 means hq1, h2 is hq2. I'm getting lazy, so I like to reduce the number of letters, subscript, which denote the metric. Cartesian coordinate is easy. h1, h2, h3 is all one, right? So Laplacian f is actually partial x squared partial f, partial y squared partial f, partial z squared partial f, right? Cylindrical coordinate.
Q1 is rho, Q2 phi, Q3 is 1, H1 is 1, H2 is rho, H3 is 1. So Laplacian F rho phi z, H1, H2, H3 is rho, right? So 1 over rho, partial rho, partial H1 over H2. So H1 is 1, right? H2, H3 is rho, partial rho, partial. Phi H2 is rho, right? So 1 over rho, right? H2, H3, H1 is all 1. So round phi, round F. Partial Z. H3 is 1. H1, H2 is rho. Partial Z, partial F, right? Oh. One more. Spherical coordinate. Q1 is R, Q2 is theta, Q3 is phi, H1 is 1, H2 is R, H3 is R sine theta. So divergence of F, R theta phi, H1, H2, H3 is R square sine theta, right? So you divide by everything by R square sine theta. Partial R, partial. Denominator is 1. But H2, H3 is R square sine theta. Partial R, partial F. Partial theta, partial 1 over R, partial theta, F 1, 3, 3, 1, so R sine theta. Partial phi, partial 1 over H3 is R sine theta. Partial phi, partial 1, 2. So R, F. We can simplify a little bit. You can still see that, right? So we can simplify a little bit. So sine theta you can move without. Oops. So sine theta, partial R square, plus partial theta, partial F sine theta, plus 1 over sine theta, partial phi, partial phi, partial. So I simplified a little bit. So basically, I think what you need, we have covered maybe everything you need to understand the vector part, vector analysis with the different coordinate system. And I hope this will help you to deal with the other class, electromagnetic theory, right? So probably they haven't covered yet up to this part, or they did? 전자장은 어디까지 배웠어요? So, 여기까지는 아니고 여기까지? Okay. So it's like you're taking the same material twice. That will help you. So that's about what we are going to cover for vector analysis. And next topic is complex variable. New chapter. So before I proceed, I'd like to talk about a little bit about number systems. I think you are familiar with addition, right? Subtraction and multiplication and division. They are called basic arithmetic operations. 4 basic arithmetic operations. And if you start with some particular number system, and then you operate these 4 things, and then you obtain the same number system, then you say that particular number system is close to 4 basic arithmetic operations. So start with some set of numbers. Then you say this particular number system, then this number system closed to basic arithmetic operations. This is very important because you need to have some number system if you like to define functions. So, I mean, it may sound like a very simple matter, but it does not. The first number system you learned is when you enter the kindergarten. You learn 1, 2, 3, 4, 5, right? So say number system, we have 1, 2, 3. This number system is called? Natural numbers, correct. Or in Korean called 자연수. And also we are using base 10 number system. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then you go to the next stage, 11, 12, right? So we are using base 10 number system because we have 10 fingers, right? So it goes back to maybe 200,000 people present. So there were cavemen. And they catch a rabbit. And there was also seamen, fishermen, they catch fish. So cavemen, fishermen. So caveman has been eating rabbit all the time, and fisherman has been eating fish all the time, and they get bored. So one day, they decide to exchange. So one rabbit for one fish. How they do that? They count fingers. Okay? So 10 rabbits for 10 fish. What do you do if you have more than 10 rabbits? You bring your friends, right? Use on his fingers. They count. So that's how our system is based on 10. What if instead of was dinosaur become intelligent? If they didn't extinguish 65 million years ago, if they had a chance to evolve into intelligent being. So what number system will they use? 6, right? Dinosaur, three fingers. So instead of us, if dinosaur, such as a velociraptor, evolved into have enough time to evolve into intelligent being, and if you're teaching math, then of course they have 3 fingers already, right? So their number system will be based on 6. So old Babylonian civilization actually used a basic 6 system. So it's very intriguing because they might have some secret connection with the dinosaur in the ancient times. I don't know. So anyway, where was I? Okay, I was not thinking about base 10. So natural numbers, you can add, right? You can multiply. How about subtract? If you subtract 3 from 2, it does not belong to natural number anymore, right? So natural number system called N is close to only multiplication. Integers. -1, -2, 0, 1, 2. So integer system, you can add, right? You can multiply. You can subtract. Still obtain integer. How about division? If you divide 2 by 3, it does not belong to integers, right? So integer z is closed to plus multiplication minus. So next system has been called rational numbers. It's based on 2 integers ratio. supposed to be known by Indians. On the other hand, the rational number system, so actually this is the first number system which is close to 4 basic arithmetic operations. So this is the first number system. Let me try to find the name of the famous author. So it is believed that this rational number system has been established around 10th century BC, about 3,000 years ago. So rational number system was established 3,000 years ago and summarized by Euclid. Element. It is believed that Euclid was around BC 5th century. 5th century BC. In China, I have to draw. Strange letters, right? It's BC 10th century. 주비산경. It's the first. So, actually, we don't know the exact date of their publication, but the Euclid element and the 주비산경 was published around similar period, around 5th to 10th century before. And the reason why there was a rapid progress around that century, 10,000 century before, about 3,000 years ago. Until then, the progress in math, number system has been quite slow. Almost 200,000 years we have known only natural numbers. And then they discovered integers. And then suddenly, about 3,000 years ago, we have established rational numbers. Because taxation. Tax. The reason why the division is important is you need to divide the land. Divide the land and calculate the area to tax people, right? So 3,000 years ago was about the time that the ancient kingdoms like Egyptians or Zhou dynasty in China was established. So they knew that the rational number was everything they need to know until the time of Pythagoras. Pythagoras, right? Pythagoras. He asked the question that, is there any number such that x squared is 2? This is a very simple question. And now we know that, right? This is called the square root of 2. So Pythagoras established a new number system called irrational numbers. So in principle, every number can be represented with the rational number, with the irrational numbers, cover everything. It's called real number. Until 18th century. I saw one newspaper, one YouTube, 지금까지는 말이죠. One particular YouTube actually started with something, and then it was not possible until now. 지금까지는 말이죠. Something like that. So until the 18th century, we have satisfied with the real numbers. But in the 18th century, there's another question. Is there any number, if you square, you get -1. There is no real number, right? So this C is called I, an imaginary number. And the mathematician is Leonard Euler. (1707–1783). So Euler is the first. Actually, there was another, like a not orthodox theory that 15th century Italian mathematics already invented imaginary numbers. Maybe Da Vinci probably knew about that, but there is no historical record. So as long as the record goes back, it's Leonard Euler who first supposed to discover that number that if you square it gives -1. Of course, you don't know, right? There was somebody already before him that knew about that. So it's called complex number. And they supposed to belong to complex number system. And this number system is close to 4 arithmetic operations. So addition and subtraction, say C1 x1 plus iy1, C2 x2 iy2. So x1, x2, y1, y2 all belongs to real number. and z1 plus minus is defined as x1 plus minus x2 plus I y1 plus minus y2. So you can define both addition and subtraction. And multiplication, z1 cross z2, z1 z2, x1 plus I y1, x2 plus I y2. You just do as real numbers. You multiply x1 and x2. And you multiply this I y1 x2. You multiply this with this I x1 y2 plus finally you multiply these two I y1 y2, and this is minus 1, right? So it becomes x1 x2 minus y1 y2 x1 y2 plus y1 x2 belongs to complex. So multiplication can be defined Am I going too fast? It's okay? Finally, division. So z1, z2, x1 plus I, y1, x2 plus I, y2. Uh-oh. So how do we define the division? What do you get if you divide one complex number by another one? So we are in a deadlock, right? Grade set. Good. I told you that in mathematics, you can do nothing by multiplying by 1, right? So let's say I'm going to multiply x2 minus I y2 and x2 minus I y2. If I do this is basically 1, right? I mean, no matter how complex numbers you have, if you divide by the same thing, you always get 1, right? Even if you don't know how to divide complex numbers, if you multiply by something and divide by the same thing, it's supposed to be 1, right? Do the same thing. So x2 plus I y2 x2 minus I x2 y2 I minus I y2 y2 x1 x2 I y1 x2 minus I x1 y2 y1 minus I y2. This cancels each other. And I times minus I is I minus 1. Minus 1 times minus 1 is equal to plus 1, right? So we have x2 square, y2 square, x1, x2 plus y1, y2, I y1, x2 minus x1, y2. Now we know, because So we have finally x2 square, y2 square, x1, x2 plus y1, y2 plus I, x2 square plus y2 square, y1, x2 minus x1, y2. So it does belong to complex numbers, right? So we have seen that this complex number is close to 4 arithmetic operations. And in the spring semester, if you have taken my class, there is another system called square matrix. And determinant A is non-zero, then the square matrix system is also close to 4 arithmetic operations. So we have, even though we have number systems starting with natural numbers, integers, the rational number system is the first one that is close to 4 arithmetic operations. After that, real numbers and complex numbers. And there are other systems called square matrix with non-zero determinant, also belongs to the, and also satisfies 4 basic arithmetic operations. Maybe take a break for a few minutes and then continue, right? So we just found out that complex numbers, you can define the division too, right? So start with x plus I, y. You define complex conjugate, just minus iy. You change the sign of imaginary number. Z square, then x square plus y square is defined as magnitude of the particular number. There are other ways to so basically the complex number z represents point in xy plane, right? The complex number z is equivalent to the point in xy plane. Then you can actually find the distance and angle. So r is square root of x square plus y square. Theta is tangent inverse y over x. Then this z, x plus iy, can be represented r cosine theta plus I r sine theta, r cosine theta plus I sine theta. This is called polar representation. Then it's very interesting to calculate these numbers, especially the multiplication. I'll just give you time to copy. So z if you multiply by z square, r square is r square cosine square theta minus sine square theta r square I sine theta cosine theta plus cosine theta sine theta. Something familiar from your middle school days. What is this? Cosine 2 theta. We know that cosine A plus B, cosine A, cosine B, minus sine A, sine B. Somewhere along the line you have learned this, right? Sine A plus B, sine A, cosine B, cosine A, sine A. Oh no, sine B. So this is sine 2 theta. So interesting thing is r square cosine 2 theta sine 2 theta. So as a homework, you can check z to the cube r cube cosine 3 theta plus I sine 3 theta. We can continue. Z to the n, r to the n, cosine n theta, sine n theta. So say r is equal to 1, and we say f theta is cosine theta plus I sine n theta, I sine theta. Then f to the theta, f to the n is cosine n theta, I sine n theta is f to the n theta. So what is this function? Say fx to the n is fnx. What is the form of this function? If you multiply by n times, then same as the function with the argument multiplied by n. Exponential function, right? So that means f theta cosine theta plus I sine theta, same as exponential I theta. This is called Euler form. I told you important name, Leonard Euler. 1707 to 1783. Another important name is Cauchy. Augustine Louis Cauchy. 1879 to 1857. And Bernard Lehman. 1826 to 1866. Three names are most important in the development of mathematics. Riemann is also famous for Riemann geometry. Cauchy. This is a very particular number, 1789. It's a year of the French Revolution. Date de Bastille. So Cauchy was born in the year of the French Revolution, and actually he made a revolutionary discovery in mathematics too. So this is a really important thing, that Euler's discovery. Euler's formula. Euler's formula. Exponential I theta is cosine theta plus I sine theta. This is one of the famous equations in called wave equation. And solution is of the form IKR. This form is really important because it's periodic. It's KR 2 pi. We get the same magnitude, right? So if R is K over E pi plus N integer, you get the same magnitude. That means this function is repeating itself at certain distance, right? The solution of electromagnetic wave satisfies this Euler's formula, Euler's form, that is propagating. So the Euler's form actually predicts that propagating solution. Allows propagating solution. So that means the light is typical propagating solution, right? It exists. Euler's formula. When Moses wrote the Bible in about 13th century BC, he started with the one sentence that there was a light in the beginning, right? This is the first sentence of a Bible. Moses was not a mathematician. If Moses knew the complex variable, he probably have written there was Euler's formula in the beginning. So the correct form, light exists because of the Euler's formula. Should be written as there was Euler's formula in the beginning. That means our universe was created such that the Euler's formula is correct, exists. So Euler's formula allows the light to exist. So I think if the mathematician wrote the Bible, he might beginning with instead of light, formula, Euler's formula, that allows the light to exist. And that's how this current universe is set up a long time ago. So, because it is getting lunch time, maybe stop here today and next week